Hey guys, it's Lexi, and in this video I'm going to be doing an introduction to resonance. So before we get into how to draw resonance structures, we're going to talk about their purpose. So resonance structures help to deal with the inadequacy of bond line structures. So for example, this is a bond line structure of butene, and you can see that it's comprised of a single bond, and then a double bond. And this is a perfectly adequate representation of butene. However, if we look now at this allylic carbocation, we can see that we've got a carbocation, and the carbocation is a single bond away from this double bond, and that means it's allylic. And so when we're trying to represent this molecule here adequately, this structure alone is not sufficient, because we know that these pi electrons that are part of the double bond here are actually not localized to this position. Instead, we can see the resonance structure here, where the resonance arrow shows that these pi electrons are partially present in this other position here. And this positive charge that right now appears to be localized to this carbon is actually also spread out to this carbon as well. And so the actual molecule has some characteristic of this resonance structure and some characteristic of this one. So no one really likes talking about MO theory, but in order to best understand resonance, it's helpful to know just the very basics of MO theory. So the first point is that electrons are going to be associated with the entire molecule rather than with individual atoms like we see when we're drawing a Lewis structure. Second, all the electrons in the entire molecule are going to occupy regions of space that are known as molecular orbitals. And third, you have two electrons that are placed in each orbital, starting with the lowest energy orbital first until all electrons occupy orbitals. Okay, so now we can connect MO theory with resonance. So this is the example that we looked at the beginning. So remember we talked about how the actual molecule is some hybrid between this molecule and this molecule, and that is represented via the resonance hybrid. So here you can see the resonance hybrid, and what you'll notice is we don't have a localized positive charge at all. Instead, we have two partial positive charges on each carbon. This is important because it shows why resonance is so important for increasing the stability of a carbocation. Remember, a carbocation is an area of electron deficiency. But rather than a single carbon atom having to bear the electron deficiency, it is spread across multiple carbon atoms. And so what we see is a partial positive on each carbon. Another aspect that you're going to notice is you don't have a double bond between carbon 1 and 2, nor do you have a double bond between carbons 2 and 3. Instead, we have a 1.5 bond throughout the entire molecule. This indicates that those pi electrons are spreading throughout that overlapping p orbital system. And so you can see that represented in the MO drawing that I tried to show you guys, where you can see that there's this overlap across the top here where these are all overlapping. And then there's also an overlap across the bottom here where they are also overlapping. And so the pi electrons that are involved in the double bond are spread throughout those p orbitals. So a common misconception that students have is they think, oh, the double bond is moving back and forth. It's kind of flip-flopping. At any moment, you might see the double bond here or you might see it there. And that is not the case. In reality, the resonance structures are not showing any sort of motion. The carbocation is not moving, nor is the double bond. But instead, the two resonance structures are giving you some insight into what the actual single molecule looks like, which is best represented through the resonance hybrid. The double bond is neither here nor there, but rather spread across the entire molecule as evidenced in the resonance hybrid. The same is true of the positive charge. It is not on the first nor the third carbon, but instead spread across both carbons. So while we just talked about how the the electrons are not actually moving in a sort of flip-flopping sense, for practical purposes, we do use resonance arrows to indicate how you should position the electrons between one resonance structure and another. And there are certain patterns or rules that you need to follow in order to practically know how to draw the resonance structures. So, resonance arrows have a tail and a head, with the electrons moving from the tail to the head. And a couple of important rules for what you cannot do when you're drawing resonance structures. Number one, you should never break a single bond. Why? Well, because resonance is showing the movement of pi electrons. These are electrons that are involved in lone pairs, double bonds, and triple bonds. They are not part of the sigma bond that exists in a single bond. So you can't break a single bond when you're doing resonance arrows. Second, you should never exceed an octet for second row elements. These are things like carbon, oxygen. You can't give them more than 8 electrons because that would be a violation of the octet rule. So here you can see an example of each of those exceptions. So the first one is showing the breaking of a single bond. So if we were to actually follow what that arrow is showing, we would be erasing this bond here, and we would essentially be cutting the molecule in half. So that's not going to be a valid resonance arrow. The second example is showing the movement of the pi electrons, and we know this carbon atom here actually has 3 hydrogens that are not shown. And so by moving the electrons down, we would be forming a 5th bond with this carbon atom. And carbon is one of those second row elements, so we can't violate the octet rule and give it more than 8 electrons. So now that we talked about how you cannot move the electrons using resonance arrows, the next video is going to discuss the 5 resonance patterns. And I really like how these are presented in the Klein textbook, so that's where this image comes from. But I'll kind of discuss examples with you guys in terms of how to utilize these 5 resonance patterns in order to draw any resonance structure for a molecule that you're given. Thanks for watching. If you have any questions, feel free to leave them in the comments below. If you enjoyed the video, make sure to give it a thumbs up, subscribe, and also hit the notification bell so that you can stay up to date when I upload new videos.